Have you ever looked up at a clear blue sky and thought about how much water is floating right above your head? Right now, Earth's atmosphere holds roughly 12,900 trillion liters of fresh water. It's an invisible ocean. But if it's up there, how do we get down here? Today, we're talking about the science of harvesting thin air. For a lot of the world, rain is a luxury. Take a look at these glowing areas on the map. Places like the coasts of Peru, Namibia, and Western Australia get less than 1 millimeter of rainfall a year. That is practically nothing. But they have a secret weapon, nightly fog. What if we could treat the weather itself as a natural resource? The Goldilocks droplet, here's the problem with fog. It's tricky. A fog droplet is tiny, only 2 to 50 micrometers across. To put that in perspective, look at the size of a human hair or a standard raindrop. Fog droplets are so small and light that they just float around obstacles instead of crashing into them. They are the Goldilocks of water droplets, not heavy enough to fall as rain, but not light enough to stay as invisible gas. So, to catch them, engineers look to nature, specifically the Namib Desert Beetle. This little guy survives in one of the driest places on Earth by doing a handstand in the morning fog. Its shell has a genius microscopic blueprint. It's covered in tiny bumps that are hydrophilic, meaning they attract water. But the valleys between the bumps are hydrophobic. They repel water. This beetle teaches us the universal principle of harvesting water from air, capture, and directional transport. First, you need a surface that grabs the tiny droplets. Second, you need a shape that forces those droplets to combine and roll down into a container before they evaporate. Think of how water runs down a smooth cone or collects on the knots of a string. To scale this up for human use, scientists developed the spiderweb approach. Using large mesh nets with tiny 1 millimeter openings, we can catch the fog as the wind blows it through. It's essentially a giant tennis net that sweats. On a good day, just 1 square meter of this mesh can pull 3 to 10 liters of water right out of the breeze. But catching the water is only half the battle. These nets are usually placed high up in the mountains where winds are fierce. A traditional flat net acts like a sail and will just rip to shreds in a storm. Newer designs, like the Cloudfisher, use a heavy-duty, 3D woven mesh suspended on a system of springs. It bends and flexes with the wind, surviving gusts of up to 120 kilometers per hour without breaking. And this isn't just theory. It's happening right now. High up on Mount Boutmezguida in Morocco sits the world's largest fog farm. It uses 31 massive net units to pull up to 37,000 liters of fresh water out of the air on a foggy day. That water is then piped down the mountain, providing a reliable, life-changing water supply to 16 different villages. Now for the catch. You can't just put a fog net anywhere. It requires a perfect geographical recipe. You need high elevation to meet the clouds. You need the right fog density and specific seasonality. Most importantly, you need perfect wind orientation. If your net is angled just 30 degrees away from the incoming wind, you lose 25% of your water yield. But what if we could make the nets better? Enter nanotechnology. Scientists are experimenting with ultra-advanced coatings that mimic the desert beetle on a microscopic scale. By using these nanotech patterns, we can achieve yields 3 to 5 times higher than standard nets. And what if there is no wind to push the fog into the nets? Active collection systems use an electrostatic magnet. By applying an electric charge to a grid, the system ionizes the air and literally pulls the charged water droplets onto a collection plate. It requires electricity, but it works in zero wind conditions. If there isn't even fog, we can look to the stars, literally. Using a process called radiative cooling, special materials beam thermal heat directly into the freezing vacuum of space. This makes the surface perfectly cold, causing the invisible water vapor in the air to condense into droplets, just like a cold soda can on a hot summer day. So how does it taste? Fog water is incredibly pure. In fact, it meets strict World Health Organization standards right out of the net. But because it has almost zero minerals, it tastes a bit flat. Local groundwater, on the other hand, is usually way too hard and full of minerals. The solution? Mix them together. Blending pure fog water with local groundwater creates the perfect, healthy community water supply. Let's talk money. When it comes to operating costs, fog water is incredibly cheap, around 25 cents per cubic meter. That easily beats energy-hungry desalination plants, and it completely crushes the massive cost of trucking water into remote villages. The upfront cost depends on the tech. A basic FogQuest net might cost $1,500, while a stormproof cloud fisher can run about $11,000. But once they are up, gravity does the rest. The water is there. It's all around us. The future of surviving droughts isn't about finding new water. It's an engineering problem. It's about mastering wettability, perfecting geometry, and letting gravity do the heavy lifting. Thanks for watching. If you thought this was cool, make sure to hit that like button, subscribe, and turn on notifications for more deep dives into the tech shaping our future.